Heat transfer occurs when there's a temperature difference between two regions. Heat moves from hot regions to colder regions. If the temperature of this side of the plate is colder than the other, the heat will transfer to the colder side of the plate. Through the plate, the heat moves through conduction, the heat transfer through solids. Atoms in the plate are imparting their energies through each other for the net movement of heat to reach the colder side of the plate. To find the heat transfer rate of conduction, we must multiply the cross-sectional area of the plate with the plate's conductivity and the temperature difference between the hot and cold regions all over the length of heat transfer. If the air is colder than the hotter side of the plate, then there will be convection, from the plate to the air. Convection is a heat transfer from a solid surface to a fluid. This is when heat is transferred to the air from the plate and molecules in the air begin to move faster and spread out. This can happen again as hot air spreads out, cold air fills the gap and is near the hot plate again to repeat convection. This is another method of heat transfer and is found by multiplying the convective heat transfer coefficient by the surface area and the change in temperature. All materials are not the same and can have different properties that change the conductivity and heat transfer coefficient for heat transfer. This demo aims to show that.
In this experiment, we aim to create a system where this equation is true in order to determine K, also known as thermal conductivity, for various materials. Being able to calculate thermal conductivity is important for a chemical engineer, as it informs them how the material can be used in the context of heat transfer, where a high K value means that it is a conductor, and a low K value means it's an insulator. In this experiment, you'll need insulation, thermocouples, a Kapton heater, a DC power supply, solid aluminum, aluminum foil, and aluminum powder. So you're going to want to wedge your thermocouples about 1/4 centimeter deep on each side. Next, you're going to place your samples into the styrofoam hole, and in case of the powder, pour it into the hole. Use the alligator clips on the wires of the Kapton heater, and plug in those wires into the two terminals of the DC power supply. Turning on the power supply and setting the voltage to 12.4 volts, we get a current of 0.322 amps, giving a total power supply of 4 watts. You will now notice that the two temperatures on your digital thermometer will begin going up. At this point, you're going to want to wait about 30 minutes for these temperatures to remain constant, meaning you're now at steady state. Once at steady state, record these two temperatures and plug them into the equation. At this point, you'll be able to calculate thermal conductivity. After finding the thermal conductivity of all three samples, we expect the following order from left to right. As our samples incorporate more air within its structure and have more surface area, the worse a conductor will become, since air is a very poor conductor and the surface of our aluminum will begin to oxidize.
For the first part of our experiment, solid 5052 aluminum was used. The solid block we created was 6 centimeters in length with an area of 1.25 by 1.25 centimeters. As previously stated, the thermocouples were placed 1/4 centimeter deep into the solid aluminum block. After waiting for the system to reach steady state, we recorded a bottom temperature of 51.1 degrees Celsius and a top temperature of 41.5 degrees Celsius. 5052 aluminum has a known thermal conductivity of 138 watts per meters Kelvin. Using the information we gathered, as well as Fourier's law for one-dimensional heat transfer, we get a final Q conducted of 3.736 watts. Interestingly, this value was very close to our Q supplied value of 4 watts. This value of the 3.736 watts will be used to help us find the thermal conductivity of both the aluminum foil and the aluminum powder.
For the next part of the demo, we used aluminum foil to compare the K value of pure aluminum to the metallic alloy. Aluminum foil with cross-sectional area 2.25 centimeters squared and length 6 centimeters. At steady state, the temperature on the side in contact with the heater was recorded as 51.3 degrees Celsius and 47.5 degrees Celsius on the side not in contact with the heater, yielding a temperature difference of 3.8 Kelvin. To solve for thermal conductivity, Fourier's law for 1D steady-state heat conduction was used and then rearranged to solve for thermal conductivity. Using Q equals 3.736 watts, area equals 2.25 times 10 to the negative 4 meters squared, length equals 0.06 meters, and delta T equals 3.8 Kelvin, a value of 262 watts per meters times Kelvin was obtained, which is relatively close to the thermal conductivity of pure aluminum at 237 watts per meters times Kelvin. This makes physical sense because we assume the foil to be composed purely of aluminum.
For the last part of our demo, we measured the K value for aluminum powder. For the powder at steady state, we measured a T hot of 34.5 Celsius and a T cold of 30.1 Celsius. The distance between each thermocouple being 4.5 centimeters, an area of 2.25 centimeters squared, and the Q value of 3.8 0.736 watts, to find a conductivity of 171 watts per meter Kelvin. Now, reviewing our demo, we found a Q conductivity for the aluminum alloy to be 3.736 watts. This is 93.4% of the heat supplied by our heater, which was 4 watts. When we use this Q value to find the conductivities for the aluminum foil and powder, we found interesting comparisons that differ from our prediction for conductivity. The foil had a higher K value than the aluminum metal alloy. This is because alloys typically have a lower conductivity than their pure monometallic counterparts, like the aluminum foil. We also saw that the aluminum powder had a lower K value than the foil. This is a result of more air gaps in surface area for aluminum oxide to form. It is known that aluminum oxide is a poor conductor, poorer than that of pure aluminum. So, our original prediction was incorrect, and the correct order of conductivity demonstrates how metal alloys and metal oxide inclusion impact conductivity for this metal.